Students, today we will be talking about a very important part in the case of the giant nerve fibers, and this is the example of the mantle ganglion in the case of the squid. So, if you go by the first diagram or the first figure on this particular page of the Edu site, so here you can see a particular squid with the mantle ganglion, and this particular image is giving you the exact position of the mantle ganglion in the case of the squid. Now, this mantle ganglion, actually it is a congregation of different kinds of the fibers. Now here the most important thing is the pre-ganglionic nerve and the post-ganglionic nerve and the interrelation in between these two. So this is very important to study. So first of all, I think I should start with the exact structure of the mantle ganglion, which is also called as the stellate ganglion in the case of the squid. Now students, go by the second diagram, and this second diagram is pertaining to the mantle ganglion of a squid. Now in this particular diagram, we start with the very left side of this diagram. Here you can find labeling which is called as GF2. Actually, these are the fibers which are present in the pre-ganglionic nerve. So this is the nerve which is penetrating the mantle ganglion from the head side. So it is coming from the head side, it is going into the mantle ganglion, and here it is labeled as the pre-ganglionic nerve on the top, if you see. Now inside this pre-ganglionic nerve we have different types of fibers. The fibers which are thin in the diameter, they are called as the accessory fibers, which are labeled here as accessory fibers, and they are in blue and black color. And one fiber which is very thick in diameter, it is labeled as GF2. So this is the giant fiber 2. So these are also called as the second order giant nerve fibers. And here we have only a single second order giant nerve fiber, which is here labeled as GF2. Now students, if we go to the right side of the diagram, here you have the post-ganglionic nerve. So this is the nerve which is coming out of the mantle ganglion, and it is going towards the hind end of the squid, as we have previously seen in the diagram 1. Now students, inside this post-ganglionic nerve you can see a GF3. Now this is a giant nerve fiber of the third order. Third order refers to that it is very thick in diameter, and it has been developed by the congregation of the giant neurons. And this particular fiber, it is ramifying, and it is giving impulses to the whole of the body of the squid, which is like for the movements in the particular animal. Now students, if you see the central part of this diagram, here we see two types of synapses. So synapses are the actual connections in between the two types of the giant nerve fibers over here. Now these two fibers are GF2, the second order fiber, and the GF3, which is the third order fiber. Now in the center you have two types of synapses. First, they are the proximal synapses. Now the proximal synapses are in between the accessory fibers and the GF3 fiber. So this is very important to note. The proximal synapses are not in between the GF2 and GF3. They are between the accessory fibers and the GF3. Now if we go to the second type of the synapses, these are the distal synapses. Now distal synapses are in between the GF2, the second order fiber, and the GF3, the third order fiber. Now these are the actual direct connections in between the giant nerve fibers of second order and third order. So we are actually concerned with these distal synapses. Too much of our studies are based upon these distal synapses in between GF2 and GF3. Now if you see the particular diagram in the very center, you have various ramifications of the distal synapses. Here we have written as L1, L2, L3, 4, 5, 6, 7, 8 and 9. So you have got 9 stellar nerves, or they are also called as the stellar nerves or stellate nerves, which are again of the you can say the third order. But still the actual third order giant fiber is the inside the post ganglionic nerve that we have described earlier. So the distal synapses, they are the actual connections. Now here if you see a very small green box made in the very center of the diagram, this is the actual connection. This is a distal synapse in between the GF2 and GF3. Now here on the below right corner, I have given you a green box in which there is a connection shown in between the second order fiber and the third order fiber. Now here the second order fiber is colored to be in orange color, and the third order fiber is in the black color. Actually it should be in the opposite direction. Actually the second order fiber here is on the lower side and third order fiber is on the top. So what is shown in this particular green box is that the third order fiber, it can penetrate the second order fiber, and there is some release of the neurotransmitters which are labeled here in green dots, as green dots. So the impulse is coming from the second order fiber, from the pre-ganglionic nerve in GF2, and that is going to this distal synapse, and through this synapse the impulse is traveling now into the GF3, the third order fiber, into the post-ganglionic nerve. So this is through the transmitters. So students, this is the actual you can say diagram which is showing you the connection in between the GF2 and the GF3 inside this mantle ganglion of the squid. So now we can explain that how the impulses can travel from the second order fibers to the stellar nerves with the distal synapses. Here you can see the distal synapse is in between the GF2 and GF3, and GF2 and stellar nerves. So even the synapses in between the GF2 and stellar nerves are distal synapses. So they are also covered under distal synapses. So students, this is a very important diagram, and you have to draw it in your examination if you get this particular question. Now if we go with the third diagram, which is very important as per the you can say the electrophysiochemical experiments are concerned. So this is a very important and beautiful diagram which is shown on the left side with the presynaptic axon and a postsynaptic axon, which are in blue and red colors respectively. So in the very center there is shown a particular area of the synapse. So this is the area where we have done all the studies about the presynaptic and postsynaptic potentials. Now students, suppose you give some potential to the presynaptic axon which is of blue color, as shown in the left diagram. Now if you give some current in the presynaptic axon, that current will flow into the stellar nerves and the postsynaptic axon, which is of red color. Now on the right side you have got three graphs. Now these graphs actually they are representing the presynaptic potentials and the postsynaptic potentials. Now when you give current in the blue presynaptic axon, some of the potential is like traveling into the postsynaptic axon through the synapses. Now these graphs they are showing the voltage in between the presynaptic knob and the postsynaptic knob. Now if we go by the A graph, the graph number A, it is showing that if you give a current in the presynaptic axon, which is shown here in blue color, an equal kind of current is developed in the postsynaptic axon. So presynaptic potential is generally or nearly equal to the postsynaptic potential. This is the normal case. And if you increase the current, if we take the graph B, now here the presynaptic potential has increased to some extent. The rise of the graph, you can see the rise of the graph. So here the presynaptic potential has increased, and on the contrary, the postsynaptic potential has also increased to some extent, and that is overriding the value of the presynaptic potential. So postsynaptic potential here is more than the presynaptic potential. This is very amazing thing to note. Now if we go for the graph C, here we increase the current. The blue arrow is like on the you can say higher level, and if you see the red arrow or the second graph, which is of the postsynaptic potential in C part, so this is again risen to more of the levels, and now it is you can say quite a lot of difference has been made in between these two graphs. So conclusively, if we go by these three graphs A, B and C, I can say that when you increase the current in the presynaptic potential or the presynaptic axon, an increased postsynaptic potential is made in the postsynaptic axon through the synapses. So this is because of the increased, I think, release of the neurotransmitters in the case of the giant nerve fiber synapses. So this is showing the effect of the presynaptic potentials from the second grade fibers on the postsynaptic potentials of the third grade fibers. So this is a very important part, and you should be very clear about these three diagrams. Now we are considering the fourth diagram, and this diagram is about the synaptic blocking of the synapse by the TTX. So TTX, actually this is a chemical which is blocking the synapses in the normal nerve fibers. So if you put some TTX or you administer TTX into a particular you can say nerve or synapse area, so that will block that particular synapse. That means TTX can block the release of the neurotransmitters to some extent. So that's how that if you give some TTX, there will be no impulse transmission in between the nerves. So TTX is called as a synaptic blocker. Now if you see the first A part of this diagram, it is showing the experimental setup in which we have got two fibers. Both are the giant nerve fibers of the squid. First is the uppermost is the second order or the presynaptic fiber. lower is the third order post-synaptic fiber, and we have to see the extent of the voltage, you can say, in between these two fibers. So what we did in this particular experiment, that we administered the TTX, which is blocking the sodium channels and ultimately blocking the release of the neurotransmitter in this particular synapse. Now, on the right side, in the B part of this diagram, you can very well see there are 4 graphs. When we administer TTX, in the very few minutes of the administration, up to the 7th minute, so first minute gone, second gone, 7th gone. Now here the first graph comes into account, that we don't have any kind of blocking in the case of the postsynaptic potentials. Now here the TTX is not able to block the giant nerve fiber systems. The TTX can block normal fibers or normal neurons, but in the case of the second and third order giant nerve fibers, even the TTX fails to block the transmission. Now how we see this in the graph 1? Now the first graph, which is shown in blue color, it is the presynaptic potential. So when we give some voltage to the presynaptic second order fiber, there is a graph given with a spike, and the upper graph, which is shown in the red color, which is showing you the postsynaptic potential, it is quite higher than the presynaptic potential. So as we have seen in the diagram 3, in the previous diagram, we had discussed this particular part, that as we increase the current, there will be increase in the postsynaptic potentials. So here also you can see an increased postsynaptic potential in comparison to the presynaptic potential, even in the presence of the TTX. So still the case is in the normal state. That means PSP is not blocked. Here PSP refers to the postsynaptic potential, is not blocked in the case of the giant nerve fibers, even by the TTX. Now come to the second graph. The second graph shows the time slot is 14 minutes after the administration of the TTX. So after 14 minutes, the PSP or the postsynaptic potential, it starts to fade out to some extent. Now after 15 minutes, we have the third graph, we have the faded postsynaptic potential. So you administer the presynaptic voltage, and there is very less kind of voltage which is transmitted to the postsynaptic fiber or the third order fiber. Now after 15 minutes, if you take a graph after 20 minutes, we get the fourth graph, which is on the lower side. So here we have the 0 PSP. That means you administer some voltage in the presynaptic fiber, so there is no postsynaptic potential formed in this particular case after the administration or after the 20 minutes of the administration of the TTX. So students, with this particular diagram, we can conclude that the TTX is a synaptic blocker. First of all, it can block the synapse as such on the spot in the case of the normal fibers. But here in the case of the giant nerve fibers, even TTX is not able to block the synapse on the spot. So it takes time. So how much time is taking? It is taking more than 15 minutes to block that particular synapse. So that was the case of the synaptic blocking by the TTX in the case of the squid second and third grade axons. So students, that was about the mantle ganglion of the squid.